Welcome back to the barn. Today we are looking at hypothesis testing for the mean. We're in the chapter about, or the chapters about hypothesis testing. And to this point, we have talked a lot about different definitions with the hypothesis testing. We haven't done any problems yet, but we've talked about writing the hypotheses, the null and the alternate hypotheses. We have talked about the type 1 and type 2 errors. The type 1 error being the bad error, the one that says that we proved what we wanted to prove even though we didn't, and so we stopped studying, and that's always the bad error. It's always okay to go back to the drawing board. So again, we've talked through some of the basic principles, but we haven't actually seen a problem. So now is when we're going to get into those problems. Now we have just a little bit more that I want to talk to you about before we actually see a problem. So let's get going with this and see if we can get into doing some problems. So when it comes down to hypothesis testing, whether it's the mean or whatever we're doing, but hypothesis testing, that type 1 error is the bad one, absolutely the bad one. We do not want to make a type 1 error. So one thing that we need to find are what we call p-values. So let's start with p-values. And a p-value is, we're going to have this written weird. Okay, so we're starting with p-values. Let me go back to last time and use a definition that we did in our last lecture, and then I'll do the p-value definition. Sorry about that. So remember from last time that we say the level of significance which is our alpha, which we should be familiar with. The level of significance is the probability allowed for creating a type 1 error. So remember, the idea is that there's always a chance that we make an error, no matter how hard we work at this, because statistics is never 100%. There's always a chance we make a type 1 error. When you're given the problem, when your boss asks you to do this, or you set up hypothesis testing on your own, you will start with what's called the alpha. And the alpha is what you are allowed, or the probability that allowed for creating that type 1 error. So someone might come to you and they say, look, I know that it can't be perfect, but I only want there to be a 5% chance of you making a type 1 error. Someone else might say, no, I want that to be better. There's only a 1% chance allowed of you making a type 1 error. So this is a probability that's given to you. Now, the p-value is the actual probability. So we say the p-value is the actual probability our test statistic creates a type 1 error. So after we have gone out and collected our data and run our tests and done everything, what comes back is a p-value which says what the probability is that we actually did create a type 1 error. Because again, we can't be perfect. So there's always a chance that we did create that type 1 error. The level of significance alpha is what we are allowed. The p-value is going to be what actually comes back after we've done the whole problem. So creating that p-value or finding that p-value is going to be important. If the p-value is the actual probability our test statistic creates a type 1 error, we don't want that error, do we? So don't we want this probability to be as small as possible? So that's just something to keep in the back of your head. We want p-value to be as small as possible. The lower that p-value is, the lower probability we have of creating a type 1 error, and the better we did in the problem. So that value needs to stay low so that we can say we did a good job. Now, when we look at p-values, we have to look at two situations. The first one is a one-tail test, and the second one is a two-tail test. So let's start with the one-tail test. Remember back to last time when we wrote our hypotheses helped us see whether we were looking at a one-tail or a two-tail. So one-tail would either be a less than or greater than, and the two-tail would be the one that just says different. So when we're looking at a one-tail test, this is what we do. We say, if the p-value is less than alpha, so we find this p-value and we've been given this alpha. So if p is less than alpha, we reject the null hypothesis. We want p to be as small as possible. If we can get p less than alpha, that's as small as we need it to get, and we can reject the null hypothesis and then say that our alternate hypothesis has been proven. Now, if p is greater than alpha, we have to keep the null hypothesis. So it all focuses on that null hypothesis. Now remember, we want p to be as small as possible, and if it is as small as we can get it, then we can reject the null hypothesis. If it can't get small enough, we have to keep the null hypothesis. Now remember what I said, that's a one-tail test. In a two-tail test, it's a teeny bit different. So it requires a little bit more work on our part. So if it's a two-tail test here, we have to say if 2p is less than alpha, we can reject the null hypothesis. But if 2p is greater than alpha, then we keep the null hypothesis. So if it's a two-tail test, we don't just deal with this p-value we want. We have to take this p-value and multiply it by 2 because of the two tails. So the 2p goes with the two tail. But you have to remember to do that. And as you get into the groove of the problem, some people forget. So it's always very important that you pay attention to what kind of test you're doing, a two-tail or a one-tail. Okay, so with that, what we're seeing is we're basically comparing these p-values to these alphas, or the 2p to the alpha. But actually, you've already found p-values. We just didn't name them p-values when you found them the first time. So we're actually ready to just jump right in now and do an example. And once it comes to the p-value, I'll show you how we find that, and you'll be like, oh, I've already done that. Not a big deal. So let me put up our first example here. Okay, so made up, right? Made up. This says the mean weight of a male camel is 1,320 pounds. I think camels in Africa weigh less. A sample of 42 male camels, male African camels, of 1,249 pounds, and the standard deviation is 192.1 pounds. Then it says test my claim at alpha equals 0.01. Phew. Now that we get to the end of the semester, we end up spending a lot of time writing down problems. Tedious. Okay, so again, made up, basically it's made up because I just bought myself a male camel this weekend. So this is all about selling one. So made up problem, the mean weight of a male camel is 1,320 pounds. I think camels in Africa weigh less. So there I'm making a statement. So as we talked about last time, there's going to be some sort of hypothesis. And there it is. I think camels in Africa weigh less. A sample of 42 male African camels have a mean weight of 1,249 pounds with standard deviation. And then it says test my claim at alpha equals 0.01. So whoever I'm doing this study for, which I suppose is myself, but whoever I'm doing this study for is allowing me a 1% chance, 0.01 or 1% chance of making a type 1 error. So they're allowing me a very small chance of screwing this problem up. So when we go to do our hypothesis testing, we want to remember that this is a 4-step process. And the first step is always the hypotheses, okay? If you want to label them, great. If you don't want to label them, it doesn't matter to me. So when we write our hypotheses, remember we're going to have the null and we're going to have the alternate. So HO and HA. Now in this, we've got to decide what variable we're studying. In our case, we're studying the mean. So we're going to start with mu. And remember that the null hypothesis is it's a blanket statement. What do we know about mu? Not what I think, what do we know? So it says the mean weight of male camels is 1,320 pounds. So mu is equal to 1,320. So remember, this is the statement of no change, just what we've been given. Now, I think, which is going to be our alternate, that camels in Africa weigh less. So I think that mu is going to be less than 1,320. Yeah, there we go. Now, before we go any further, okay, what I want you to do is look at the numbers we've got here. So we wrote our hypotheses. Now the number 1249, that is less than 1,320, isn't it? Okay, it is most definitely less. But is it less than enough? Is it fully less than enough that we are able to say, beyond a reasonable doubt, beyond 1%, okay, chance of screwing this up, that it's less than enough? What if I just ended up getting a whole bunch of really skinny camels from, one area and there was no food there to eat, and so that's why they're all skinny? So there's always the possibility we did screw this up. So we cannot just look at this number and say, oh yeah, that's less than that, we're done. That's what requires the whole testing thing. Okay, now the second step is to find our test statistic. And this test statistic, this is our z-score. Okay, so this is z. And in this problem, we need to decide what we're doing here. So it is the mean, right? And we have a sample of 42. So that does mean that we're looking at a z-score, doesn't it? Now, if that sample was smaller, we might not be looking at a z-score. But in this case, we've got a sample of 42, so we'll use a z-score. And we can find our z-score, our test statistic, for this particular problem. So we'll say z equals, we start with the sample mean from our sample, so 1249. Subtract the original, 1320. Divide by the standard deviation, 192.1, divided by the square root of 42. remember parenthesis, parenthesis. And let's stick that into our calculator. Oops, not in the right spot. 1249 minus 1320, enter, divided by. I got negative 2 point, if we round, 40. So our test statistic is negative 2.40. Now we can also put that on the normal graph, on our little normal curve. Okay, so negative 2.40 would be over to this side. Now we're ready for our third step. And the third step is to find the p-value. But as I said, we've already done this before, we just didn't call it a p-value, and we're already halfway there. This green portion right here is your p-value. And how did I know that it was this portion and not maybe that portion? We come back to the problem, the less than, less than. So once we put our test statistic on there, we have to decide which way to shade. And in this case, because of our alternate hypothesis, we're going to shade a less than. So our p-value is actually the area of a tail. Okay, so we're just looking for the area of a tail. Now, we've done this before. If you know your boundaries, can we find the area of a tail on the normal curve? So can we go normal, excuse me, CDF, and then bottom boundary would be negative 10,000 on this guy, to the upper boundary of negative 2.40. And hopefully you got what I got. So take a second, stick that in the old calculator. Hopefully you got 0.0082. Now, of course, that's the way it pops out in your calculator, but we want to make sure that we label it. This value, this tail, is our P. So we can just say capital P equals 0.0082. Oh, right. Then the fourth thing we have to do is we need to decide if we're going to keep or reject the null. And that comes from the comparison here. So remember, we look here to see that this is a one tail, right? One tail, a less than tail. So we strictly need P and we need alpha. Now we've got a P that is 0.0082, and isn't that less than our alpha of 0.01? So our probability of creating a type 1 error was less than 1%, not a lot, but a little bit less than 1%. We were allowed 1% though. So our probability came in under what we were allowed. So we did a good job, didn't we? We proved beyond a shadow of a doubt that what we wanted to show is true. So we get to reject the null. And then, oops, I said this was a 4-step process, but I forgot the 5th step. Remember, the 5th step is, I mean, obviously the work was important, but the 5th step is most important when you're giving this to the public. So remember, the 5th step is to write a sentence, to make a summary. So we need to write this in a sentence, and this is what our sentence will look like. Just like when we did confidence intervals, it's the same idea here, same idea. Get in the habit of writing the sentence and it will start to make sense. So we can say, there is enough evidence to show male African camels weigh less at alpha equals 0.01. So when we write our sentence, we kind of hedge our bets a little bit. We don't say, we proved. We say, there is enough evidence. And by saying there is enough evidence, we're saying, we proved beyond a shadow of a doubt. We did a good job, okay? But are we 100% sure? No. There is enough evidence to say that the male African camels weigh less, okay? So we're hedging our bets so that we're not putting out there something where someone can go, you're wrong. You're like, hey, we only said there's enough evidence. And then we tell people what alpha we were allowed. Now, if you're giving this to the public, a lot of times we'll leave that off. We can just say there's enough evidence to show that male African camels weigh less, okay? But anybody that's doing a statistical test wants to see what your alpha was that you were allowed. So at 1%, and then they go, oh, okay, you actually did a good test. All right. But that sentence there is very, very important. So there is enough evidence to show male camels weigh less at alpha equals 0.01. Okie dokie. Shall we look at the next one? So we did our first hypothesis testing. Now again, the process works the same each time. Follow the steps and you hopefully won't forget anything. So let's see what I got this time. I believe my stats students score better than 72 points on a test. Oops, I forgot. I always hate when I read this. Better than a mean 72 points on a test. Sorry. A sample of 26 students have, I guess that's has, a sample has a mean of 72.8 and a standard deviation of 2.6. Test my claim at alpha equals 0.05. Little bit different setup in the way that this one is written to start us off. So in this one, I go right into my claim or my belief. I believe my stat students score better than a mean 72 points on a test. Okay, so no blanket statement to start with, but it's kind of built into that first sentence. Then we've got our sample of 26 students, but anybody seeing an issue with that? 26 students means we are not normal, are we? So because of this, are we using Z or T? All of a sudden, we're thrown into T. Now, believe it or not, if we can do it with Z, we can do it with T. Not a big deal, okay? Don't let that bother you. You just have to make a note of it. Okay, so our sample of 26 students has a mean of 72.8 and our standard deviation of 2.6. And now I want to test the claim at an alpha of 0.05. So I'm allowing myself a 5% chance of making that type 1 error. 5% chance. Now, just because it's a T doesn't change much. We start the process the same way. So the first thing we do is we find our hypotheses. Now, even though I forgot the word in there, I meant to put it in there. sorry. So we're looking at the mean here. Hey, the light just came on. So in this case, I actually already have my alternate. I believe my stat students score better than a mean 72. So that's actually the alternate just given right to us. I think the mean is better or greater than 72, which means that we can just go with our null hypothesis as being equal to. We don't even need the less than part, just equal to. So these two numbers should always be the same. It's only these guys that should be different. Okay, so the second step is that test statistic. Now in our last example, our test statistic was a z-score, but in this example, our test statistic is going to have to be a t-score. Okay, so we need a t-score. Now, we haven't done this before, but the nice thing about it is a t-score basically is the same formula as a z-score, okay? Just using a different letter. So I'll write the formula here. T equals x bar minus mu all over s over the square root of n. So the nice thing about it is it follows the same process. It's just a t instead of a z. And then the other thing to keep in mind here is we want to go to 3 decimal places on this guy. T's are 3, Z's are 2. But we're going to find our test statistic the same way we did last time. So we'll start with t equals, and we start with our sample mean, so that's going to be the 72.8, minus the original, which was 72. Now again, I want you to look at those two numbers. 72.8 is definitely bigger than 72, but is it bigger than enough? Did we prove beyond a reasonable doubt that 72.8, that my stat students did better? Let's see. Okay. So 72.8 minus 72 over the standard deviation, 2.6, over the square root of our 26. So remember the point there and the 26 there. And we stick that into the calculator. Uh, 2.6. And I got, this time, 1.569. Remember, 3 decimal places on this guy. Okay, so 1.569. And remember that we can also put that on our graph. 1.569. And then remind me which way we're shading this time if we were going to set this up. So I want this graph to represent better than. So from our t-score, are we going to go this way? Okay. So now we need a p-value. So what step are we on? On the third step here. So p-value. And this is where things are going to change. We know that this over here is our p-value, right? We know that's our p-value. The problem is that we can't use the normal CDF because was this normal? Okay, so we need to use something that has to deal with t's. So on your calculator, what we need to look for is the t-CDF, okay, t-CDF. And the nice thing about the t-CDF is it's right next to the normal CDF. So let me show you here real quick. Okay, so if we go second distribution, like we've done time and time before, here's the normal, normal, inverse normal, inverse t. Hold on a second, you guys, I'm gonna have to take a break.